The Sun has just unleashed its most powerful solar flare of the year, sending intense radiation across millions of kilometers of space. But the eruption may not be the final event. The same unstable region remains active, filled with twisted, magnetic fields capable of releasing even more energy. In this documentary, the journey follows the flare from the Sun's surface to Earth's upper atmosphere, revealing what happened, what may come next, and how vulnerable modern technology can be. Like the video, subscribe to the channel and begin the journey into the heart of the Sun. Far beyond Earth's atmosphere, the Sun and its planets occupy a moving region of space, shaped by light, plasma gravity, and magnetic fields. At the center, the Sun releases energy continuously, sending visible light, infrared radiation, ultraviolet radiation, X-rays, charged particles, and a persistent solar wind outward in every direction. Earth travels through this environment at an average distance of about 150 million kilometers, protected partly by its atmosphere and partly by its magnetic field. Most solar activity passes without serious consequence at the surface. Even strong events remain separated from ordinary life by distance and by layers of natural shielding. Yet instruments in space and on the ground record the changing Sun in detail, because brief eruptions can alter the conditions between the Sun and Earth within minutes. During the present period of activity, a large and magnetically complex sunspot group known as active region 43666 becomes the source of an exceptionally powerful flare. The event reaches the X8.1 class, placing it among the strongest eruptions measured during the current solar cycle, and making it the largest flare recorded during the year so far. Solar flare classes describe the peak intensity of X-rays detected near Earth. The main categories rise from A through B, C, M, and X, with each category representing a tenfold increase over the one below it. Within the X category, the number gives a finer measure of strength. An X8.1 flare therefore produces a much greater X-ray intensity than an X1 flare, although the full physical importance of any event also depends on its duration, location, associated particles, and any eruption of solar material. From the scale of the solar system, the flare is a sudden change in the Sun's radiative output rather than an explosion that spreads evenly through all space. The visible disk of the Sun presents only one hemisphere toward Earth at any moment. Active region 4366 lies on the Earth-facing side when the flare occurs, allowing its high-energy radiation to travel directly across interplanetary space. It moves as electromagnetic energy, crossing the distance at the speed of light. The broad Sun-Earth environment, therefore, responds in stages. Light arrives first, while accelerated particles and clouds of plasma move more slowly and may follow different magnetic routes. The flare itself lasts for a limited time, but its place within solar activity is less isolated. Active regions often produce repeated eruptions because their magnetic fields remain complicated after one release of energy. Some magnetic stress disappears during a flare, while other stressed structures can remain. New magnetic flux may continue to emerge from below the visible surface, and motions in the solar atmosphere may keep twisting or pressing field lines together. For this reason, a major flare does not necessarily mark the end of activity. Observations show that active region 4366 continues to produce strong emissions and remains capable of further events while its magnetic structure stays intense. Forecasts express this as probability rather than certainty, because the precise timing and strength of future flares cannot be predicted with complete confidence. Across the space between the Sun and Earth, the background environment is already active before the flare begins. The solar wind fills interplanetary space with thin, electrically charged gas. Embedded magnetic fields stretch outward from the rotating Sun, forming a large spiral pattern. Earth's magnetic field stands within this flow and creates a cavity called the magnetosphere. The flare's first influence does not require the solar wind to carry it. X-rays and extreme ultraviolet radiation pass through the existing plasma with little delay and reach the day side of Earth after roughly 8 minutes. At the same time, solar observatories view the brightening directly and measure its changing intensity. These measurements allow scientists to classify the flare and estimate its immediate effects. The event belongs to a broader phase of the Sun's 11-year cycle. During each cycle, solar magnetic activity rises toward a maximum and later declines toward a minimum. Near maximum sunspots become more numerous, active regions become more common, and strong flares occur more frequently. Individual regions can appear suddenly grow rapidly and produce several eruptions within a short interval. A year that has already contained powerful solar events can still produce a new, strongest flare, and that record can change again before the year ends. The title of largest flare of the year is therefore temporary by nature, tied to observations made up to the present date. At the widest scale, the X8.1 flare is both immense and contained. Its energy release is enormous compared with human power systems, yet the Sun itself is scarcely altered. The Sun continues to shine through nuclear fusion in its core, producing vastly more energy every second than any single flare releases. The flare is instead a sharp rearrangement in the outer magnetic atmosphere. It changes radiation levels along the Sun-Earth line and briefly disturbs the space environment around the planet. Its influence is important because modern technology extends beyond the surface into regions where natural shielding is weaker and where radio signals depend on the electrical state of the upper atmosphere. Seen from Earth, the Sun remains a small bright disk, and the flare cannot be viewed safely with ordinary eyes. Spacecraft monitor X-rays, ultraviolet light, energetic particles, magnetic fields, and solar images. Ground stations observe radio effects and changes in Earth's magnetic environment. Together, these systems show the event not as a single flash, but as a connected disturbance moving through a vast and structured region. Within that region, distance provides time but not equal time for every effect. Material eruptions, when directed toward Earth, require many hours or several days. At this outermost level, the essential picture remains steady and clear. A magnetically active part of the Sun releases an unusually strong burst of energy. The burst travels through the shared space between the Sun and Earth. Earth receives the event through layers of distance fields and atmosphere, while the active region continues to evolve on the rotating solar surface. The first measurable influence of the flare leaves the Sun as electromagnetic radiation. This radiation includes a broad range of wavelengths, but the most important for the immediate response are X-rays and extreme ultraviolet light. Both forms carry energy through space without needing air gas or any other material to transport them. They move outward at the speed of light, crossing the distance between the Sun and Earth in about 8 minutes. By the time instruments near Earth detect the sudden rise, the flare on the Sun has already begun to change. The observed signal is therefore a delayed view of an event that has already unfolded for several minutes. The radiation does not travel as a compact shell with a sharp physical surface. It spreads outward from the active region beyond the Sun. From the scale of interplanetary space, the flare appears as a temporary increase in the amount of high-energy light moving through the solar system. The increase is strongest along directions with a clear view of the active region. Earth receives that light because the region lies on the visible solar hemisphere. Other planets and spacecraft receive different amounts depending on their positions, the angle of the source, and whether the Sun blocks the direct path. Visible light from the flare may also increase in limited areas, but the strongest immediate signature appears at shorter wavelengths. X-rays carry more energy per unit of light than visible light, while extreme ultraviolet radiation lies between ultraviolet and X-rays in energy. These forms of radiation interact strongly with atoms and molecules when they reach dense matter. In the near vacuum between the Sun and Earth, however, there are too few particles to absorb much of the energy. The radiation, therefore, crosses interplanetary space with little weakening beyond the natural spreading that occurs as it moves farther from the source. The intensity measured near Earth depends on how much energy reaches a given area. As radiation expands outward, the same total energy is distributed across a larger region. This causes the intensity to decrease with distance. Even after that decrease, a major flare remains powerful enough to produce a rapid rise in X-ray measurements. Solar satellites carefully record the changing signal continuously. The highest measured X-ray level determines the flare class, while the shape of the rise and fall shows how quickly energy is released and how long the strongest phase continues. The X8.1 classification describes the peak in a specific X-ray band measured near Earth. It does not describe every wavelength in the same way, and it does not capture the full energy of the event. A flare may rise rapidly, remain intense for a short interval, and then fade, or it may decline more slowly over a longer period. Two flares with similar peaks can therefore deliver different total amounts of radiation. The classification remains useful because it provides a consistent way to compare the immediate strength of many events using the same measurement. As the radiation moves through interplanetary space, it passes through the solar wind. The solar wind contains electrons, protons, and heavier ions at very low density. These particles do not form a solid barrier. Most of the flare's X-rays and extreme ultraviolet light continue through the thin plasma without being scattered or absorbed. Magnetic fields carried by the solar wind also do not bend the path of the light in an important way. Charged particles respond to magnetic fields, but electromagnetic radiation in open space continues in nearly straight lines, unless it encounters matter or strong gravitational effects. The path from the Sun to Earth is not perfectly empty or perfectly still. Dust grains, gas atoms, plasma, structures and magnetic disturbances occupy the region, but their combined effect on the arriving flare light is small. The radiation reaches Earth with a pattern that still reflects the changing source. Rapid brightening at the Sun appears as rapid brightening in satellite measurements after the travel delay. Small changes in emission can also be preserved, allowing instruments to study the flare's development without being close to the active region. Several spacecraft observe the event from different locations. Some remain near Earth while others move along separate solar orbits. Their viewing angles provide a broader picture of the flare and the active region. A spacecraft located far from the Sun-Earth line may see the source from the side, or it may see part of the region hidden behind the solar edge. Differences between measurements help scientists determine the shape, position, and timing of the emission. These observations also reveal that the apparent strength of a flare can depend partly on geometry. The radiation crossing space carries information as well as energy. Its spectrum shows how much light is present at different wavelengths. Certain wavelengths form in plasma at particular temperature ranges, so changes across the spectrum reveal conditions within the emitting region. Strong X-ray output indicates very hot plasma, often reaching many millions of degrees Celsius. Extreme ultraviolet images show structures at several temperatures and trace the changing shape of bright loops and surrounding material. During the journey to Earth, this information remains encoded in the arriving light. The crossing time is short compared with the slower motion of solar material. No warning based on direct detection near Earth can arrive before the radiation itself, because the information and the disturbance travel together at the same speed. Solar telescopes can identify growing magnetic complexity before a flare, but they cannot state the exact moment of release. Once the flare begins, instruments near Earth record its radiation only after the 8-minute journey is complete. Across the wide gap between the Sun and Earth, the high-energy light remains the earliest messenger. It moves quietly through the thin solar wind, spreads across an expanding volume, and preserves the timing of the source. By the time it reaches the planet, the radiation still carries the sharp signature of the flare across the broad and nearly empty distance of surrounding interplanetary space. When the flare's X-rays and extreme ultraviolet light reach Earth, they first encounter the outer edge of the planet's atmosphere on the sunlit side. At this height, the air is extremely thin, yet it is not empty. Scattered atoms and molecules of oxygen, nitrogen, and other gases remain present across a vast region. The incoming radiation carries enough energy to alter these particles directly. It removes electrons from some atoms and molecules, creating electrically charged particles called ions. This process, known as ionization, changes the upper atmosphere within moments of the radiation's arrival. The effect begins high above the weather clouds and winds familiar near the surface. The upper atmosphere extends for hundreds of kilometers, gradually blending into near-Earth space without a sharp boundary. Density falls steadily with height, but the remaining particles still absorb selected wavelengths of solar radiation. X-rays and extreme ultraviolet light do not pass freely through all atmospheric layers. Their energy is captured by particles at different altitudes depending on wavelength, density, and composition. A strong flare increases this energy, suddenly causing the sunlit upper atmosphere to become more highly ionized than usual. Only the side of Earth facing the sun receives the flare's radiation directly. The planet blocks the light from reaching the night side, forming a broad shadow through space. As Earth rotates, the boundary between daylight and darkness moves across the atmosphere, but the flare's brief peak affects mainly the region illuminated at that time. Areas near the center of the sunlit hemisphere receive radiation from a more direct angle. Near sunrise and sunset, the light travels through a longer atmospheric path, and its effects are distributed differently through the thin gases. The ionized region is part of the ionosphere, a broad atmospheric zone in which solar radiation regularly creates charged particles. The ionosphere is not a separate solid shell. It overlaps several named layers of the upper atmosphere and changes continuously with altitude, time of day, season, latitude, and solar activity. Under ordinary conditions, sunlight produces ionization during the day, while electrons gradually recombine with ions after darkness arrives. During a major flare, the balance shifts quickly because the incoming high-energy radiation creates additional charged particles faster than normal. The lower part of the ionosphere responds especially strongly to increased X-rays. Although this region contains more neutral gas than the layers above, ordinary X-ray levels are limited. During the flare, the enhanced radiation penetrates downward and produces a rapid rise in free electrons. Higher regions also respond to extreme ultraviolet light, though their behavior depends on the wavelengths present and the existing state of the atmosphere. The result is not uniform. Each altitude receives and absorbs a different portion of the flare's energy. creating a layered pattern of change across the dayside sky. At high altitudes, some freed electrons move along Earth's magnetic field, while ions respond more slowly because of greater mass. Collisions become less frequent as density decreases, allowing charged particles to remain separated longer. Even so, the flare does not create an entirely new atmospheric system. It strengthens processes that sunlight already maintains every day above the illuminated planet. Temperature in the upper atmosphere does not behave like temperature near the ground. Individual particles can carry high energy even when they remain widely separated. During the flare, absorbed radiation increases the energy of electrons and ions, but the immediate disturbance is primarily electrical rather than a simple warming of the entire atmosphere. The added ionization changes how the region interacts with radio waves, satellite signals, and electric currents. These effects appear rapidly because electrons are light and respond quickly to incoming energy and electromagnetic forces. The atmosphere also protects the surface. Most flare X-rays and extreme ultraviolet radiation are absorbed high above the ground. They do not travel through the full atmospheric column in dangerous amounts. People, animals, oceans, forests, and buildings remain beneath dense layers of air that block these wavelengths. The event, therefore, produces no sudden beam of X-rays at ground level. Its presence is detected mainly through instruments, changes in the ionosphere, and effects on technologies that use or pass through the upper atmosphere. Scientists observe the response with several methods. Satellites measure the incoming solar radiation before much of it is absorbed. Ground-based receivers monitor signals that travel through or reflect from ionized layers. Networks also measure changes in the electrical properties of the atmosphere and in currents flowing through near-Earth space. By comparing the timing of the flare with the timing of atmospheric changes, researchers confirm the close connection between the sudden radiation increase and the rapid dayside response. The strength of the response depends on more than the flare's class. The duration of the X-ray emission matters because a longer event supplies energy over a greater interval. The solar angle matters because it changes the path through the atmosphere. The previous condition of the ionosphere also matters since the region may already be disturbed by earlier solar activity. Local time season and geographic position shape the measured effect. For this reason, the same flare can produce different changes at different stations across the sunlit hemisphere. As the flare intensity rises and then declines, the upper atmosphere follows with its own timing. Ionization can increase rapidly during the strongest radiation. After the incoming energy weakens, electrons begin to recombine with positive ions, reducing the disturbance. Recovery is not identical at every altitude. Dense lower regions can change quickly because collisions are more frequent, while thinner upper regions may remain altered longer. The atmosphere gradually returns toward its ordinary daytime state, although continuing solar emissions can sustain part of the change. Across the day side of Earth, the flare is therefore received not as visible fire, but as a sudden rearrangement among invisible particles. The upper atmosphere absorbs the high-energy light, creates additional ions and electrons, and shields the dense world below. Its response is broad-layered and temporary, spreading across the illuminated hemisphere while remaining closely tied to the changing radiation arriving from the sun. As the flare strengthens ionization on Earth's sunlit side, high-frequency radio communication begins to change. These radio waves usually travel far beyond the horizon by interacting with the ionosphere. A transmitter sends a signal upward, and the signal reaches charged layers high above the ground. Under suitable conditions, part of the wave bends back toward Earth, allowing communication across oceans, deserts, mountains, and remote regions without a chain of relay towers. During a strong solar flare, this path becomes less reliable because the lower ionosphere suddenly contains many more free electrons than before. The most important change occurs in a low region of the ionosphere, where the atmosphere is still dense enough for frequent collisions. Electrons created by flare X-rays move under the influence of an incoming radio wave, but they repeatedly collide with neutral molecules. These collisions take energy from the wave and convert it into random particle motion. Instead of passing through the region and returning from higher layers, part of the radio signal is absorbed. When absorption becomes strong, distant receivers hear fading distortion or complete loss of communication. This disturbance is called a radio blackout. The term does not mean that every radio system on Earth stops working. It refers mainly to high-frequency communication affected on the daylight side of the planet. High-frequency signals occupy a range commonly used for long-distance aviation, maritime operations, emergency services, military communication, broadcasting, and contact with remote stations. These systems depend strongly on ionospheric conditions because their signals often travel by repeated paths between the upper atmosphere and the surface. The blackout begins soon after the flare's high-energy radiation reaches Earth. Since the X-rays travel at the speed of light, there is little practical warning after the eruption is detected. The strongest disruption often follows the rise of the X-ray signal and affects regions where the sun stands above the horizon. The geographic pattern, therefore, covers much of the sunlit hemisphere rather than the entire globe. Stations on the night side remain shielded from direct flare radiation, although they may still experience ordinary changes associated with local ionospheric conditions. The severity of a blackout is described through operational scales that connect solar X-ray intensity with expected communication effects. A very strong X-class flare can produce a widespread and significant disturbance on the day side. At lower frequencies within the high-frequency range, absorption is usually stronger because the wave interacts more efficiently with the increased electron population. Higher frequencies may remain usable, though their performance can still change. Radio operators often adjust frequencies during disturbed conditions, searching for channels that suffer less absorption. The exact response varies from place to place. Sunlight angle affects how deeply flare radiation influences the atmosphere. Near the center of the day side, where solar rays enter more directly, the increase in ionization can be especially strong. Near the edge of daylight, the rays cross a longer atmospheric path, and the disturbance may differ in depth and intensity. Existing ionospheric conditions also matter. Seasonal changes, latitude, local time, and previous solar activity shape the background through which the flare acts. A radio blackout is different from interference caused by electrical equipment, thunderstorms, or crowded broadcasting channels. It is also different from a failure of the transmitter or receiver. The equipment may remain fully functional while the natural path between stations becomes temporarily unsuitable. This distinction is important for operators who rely on high-frequency links. When many distant stations lose contact at nearly the same time across the daylight hemisphere, the shared cause can be traced to the changing ionosphere rather than to separate technical faults. Aircraft on long routes sometimes use high-frequency radio where ground-based communication networks are limited. Ships at sea may also depend on it beyond the reach of coastal systems. Polar regions can be especially dependent on radio and satellite links because conventional infrastructure is sparse. During a flare-driven blackout, crews may shift to alternative frequencies, satellite communication, or planned procedures. The event does not remove every option, but it reduces the reliability of one important communication method during the strongest phase. Ground observers can measure the blackout by transmitting stable signals and recording how their strength changes. Some systems monitor very low-frequency signals which respond differently and can reveal sudden changes in the lower ionosphere. Other receivers track high-frequency paths over known distances. When the flare begins, measurements show rapid absorption, altered reflection heights, and changes in signal quality. These records allow scientists to compare atmospheric response with X-ray observations made by satellites. The duration of the blackout follows the duration of enhanced radiation, though not with perfect precision. A flare that rises and falls quickly may cause a brief disturbance. A longer flare can maintain strong ionization for a greater period. After X-ray levels decline, electrons begin to recombine with positive ions. Absorption weakens as the lower ionosphere returns toward its ordinary daytime condition. Communication may recover gradually rather than instantly, and different frequencies can recover at different rates. Repeated flares from the same active region can produce repeated blackouts over several days. Each event arrives when a different part of Earth faces the Sun, so the affected geographic area changes with the planet's rotation. A region that lies in darkness during one flare may lie in daylight during another. Continuous monitoring is therefore important while a complex sunspot group remains active. Forecasts can describe the likelihood of further flares, but the precise moment of a radio blackout remains tied to an eruption that cannot be timed exactly in advance. Within the ionosphere, the process remains simple in outline. High-energy sunlight creates extra electrons. Dense, lower air forces those electrons into frequent collisions. High-frequency radio waves lose energy while passing through that altered layer. Long-distance paths weaken or disappear until the flare radiation fades and the charged particles recombine. The result is a temporary silence across parts of the daylight hemisphere, produced not by damage at the surface, but by a brief change in the electrical structure of the air far above it. Above most of Earth's atmosphere, satellites move through a region where solar radiation arrives with far less shielding than it receives at the surface. These machines circle the planet at many altitudes and inclinations, supporting communication, navigation, weather, observation, scientific research, mapping timing, and national infrastructure. A major solar flare changes their environment almost immediately. X-rays and extreme ultraviolet light reach near-Earth space after crossing the distance from the Sun, and spacecraft on the sunlit side receive the increased radiation before the dense atmosphere below absorbs most of it. A satellite does not experience the flare as heat spreading evenly across its structure. The most immediate effects appear in sensors, electronic components, charging conditions, and the surrounding upper atmosphere. High-energy photons enter exposed instruments and materials. Some pass through thin outer layers, while others deposit energy by releasing electrons from atoms. The response depends on the spacecraft's design, shielding orientation, altitude, and the sensitivity of each system. Modern satellites are built with solar activity in mind, yet no design removes every disturbance from an event of unusual strength. Scientific instruments can become temporarily overwhelmed by the sudden rise in radiation. Detectors intended to measure faint X-rays, ultraviolet light, or energetic particles may receive signals far above their normal background. Images can contain bright streaks, scattered points, or saturated regions when charged particles and photons strike the detector directly. Automatic systems may reduce exposure times close. Protective covers change operating modes or suspend observations. These actions do not always indicate damage. They often represent planned protection while the environment remains disturbed. Communication satellites depend on stable electronics and accurate control. During a flare, direct radiation can create brief electrical changes within microelectronic circuits. A charged particle or energetic photon may deposit enough energy to alter the state of a memory cell or processor. Such an event is called a single event effect because one interaction produces a local electronic change. Many of these changes are corrected by error detection systems, redundant computers, or a controlled restart. More serious failures are possible, but they are less common and depend on energy, shielding, and component design. Solar panels also receive the flare's radiation, although a single event usually causes only a small part of the gradual wear accumulated through years in space. Energetic particles can damage the crystal structure of photovoltaic cells, reducing their efficiency over time. The flare's light alone is not always the main source of long-term degradation. Particle events associated with active solar regions can be more important. Engineers, therefore, monitor both the immediate X-ray burst and any later increase in energetic protons or electrons. Spacecraft surfaces can develop electrical charge as they interact with sunlight, plasma, and energetic particles. Different materials may charge at different rates. If the difference becomes large enough, an electrical discharge can occur across a surface or within an insulating layer. A discharge may introduce noise, interrupt electronics, or damage a component. The risk depends strongly on the surrounding particle population and the satellite's orbit. The flare changes one part of this environment quickly, while later particle disturbances can alter charging conditions over longer periods. Navigation satellites require extremely precise clocks and stable radio transmission. Their signals cross the ionosphere before reaching receivers on aircraft, ships, vehicles, survey equipment, and mobile devices. The satellite itself may continue operating normally while the changed atmosphere introduces delays and errors into the signal path. Position calculations depend on the travel time from several satellites. When ionization changes rapidly, the estimated distance can become less accurate unless receivers apply corrections. Systems using multiple frequencies can measure part of the ionospheric delay and reduce the resulting error. Satellites in low Earth orbit move through the outer atmosphere where a small but measurable amount of gas remains. Extreme ultraviolet radiation heats and expands this region during increased solar activity. Atmospheric density can rise at orbital heights. The added gas produces more drag, slowing spacecraft slightly and lowering their orbits. One flare does not always create a large orbital change, but repeated activity can make predictions less certain. Operators track spacecraft carefully and may plan small maneuvers to maintain altitude or avoid close approaches. The response differs across orbital regions. Low satellites circle within the expanded upper atmosphere and experience changing drag. Navigation constellations occupy higher paths and depend on accurate timing and stable signal geometry. Many communication and weather satellites remain near geostationary orbit where they circle at the same rate that Earth rotates. At that distance, atmospheric drag is negligible, but the spacecraft is more exposed to changing particle populations and charging conditions. Highly elliptical or polar orbits pass through several magnetic environments during each revolution. Ground controllers receive streams of engineering data that describe voltage, temperature, current, computer status, pointing, battery condition, and instrument health. During strong solar activity, teams compare these measurements with space weather alerts. A spacecraft may enter a safe mode, turning away from sensitive operations and maintaining only essential functions. Some decisions are automatic, while others are made from the ground. The purpose is to preserve stability until radiation levels return toward normal. Not every satellite shows a measurable problem during a major flare. Many continue operating without interruption. Their resilience comes from shielding, careful component selection, redundant systems, software correction, and operational planning. The number and severity of effects also depend on whether the flare is accompanied by energetic particles and whether those particles reach the spacecraft's orbit. A strong X-ray classification does not guarantee serious satellite damage. Above the atmosphere, the flare becomes a test of systems built to function inside a changing, star-driven environment. Satellites remain exposed to radiation that the air below absorbs. Their instruments may saturate. Their electronics may register brief errors, their signals may pass through a disturbed ionosphere, and their orbits may feel changing atmospheric drag. Most effects are managed through design and monitoring, yet the event reveals how closely modern machines depend on the variable conditions surrounding Earth. This dependence persists across orbital heights throughout both short and extended missions. Near Earth, the flare's light is only one part of the changing solar environment. Strong activity on the Sun can also accelerate charged particles to very high energies. These particles include protons, electrons, and heavier atomic nuclei. They do not move as a single solid cloud, and they do not all arrive together. Their paths depend on energy, electric charge, magnetic fields, and the structure of the solar wind between the Sun and Earth. Some travel outward rapidly, while others become scattered, delayed, or redirected before they approach the planet. The fastest solar particles can reach near-Earth space in tens of minutes, though many require several hours. Their speed remains lower than the speed of light, so they arrive after the flare's X-rays and extreme ultraviolet radiation. This difference helps separate the immediate radiative event from a later particle event. A strong flare can occur without producing a major particle storm at Earth, and a large particle storm can depend on conditions beyond the flare's peak, X-ray class. The connection is real, but it is not automatic. Particles gain energy where magnetic fields change rapidly. In active regions, magnetic reconnection can release stored energy and accelerate electrons and ions. Shock waves driven by a fast coronal mass ejection can also accelerate particles over a much larger region. These shocks move through the solar corona and solar wind repeatedly, scattering charged particles and raising their energy. When the magnetic connection between the acceleration region and Earth is favorable, particles can follow field lines toward the planet. The solar wind carries the Sun's magnetic field outward into interplanetary space. Because the Sun rotates, these field lines form a broad spiral rather than straight radial paths. Charged particles tend to move along the field while also spiraling around it. Their motion resembles scatter the particles, changing their direction and delaying their arrival. As a result, detectors near Earth often record a gradual rise rather than a single sharp pulse. The most common high-energy particles in a solar event are protons. Electrons can arrive earlier because they move faster at comparable energies, and their early detection sometimes indicates that a broader particle event is developing. Heavier ions, including helium nuclei and less abundant elements, provide information about the source plasma and the acceleration process. Their relative amounts and energy ranges help scientists distinguish between particles released directly from a flare region and particles accelerated by a moving shock. Near Earth, satellites measure these populations with instruments that count particles and estimate their energy. Some detectors face different directions to determine where the particles are coming from. Others separate electrons from protons or identify heavier nuclei. Measurements from several spacecraft reveal how the event spreads across space. A particle increase seen near Earth may be weak or absent at another location because the spacecraft follows a different magnetic connection to the Sun. Earth's magnetic field provides an important barrier. Most incoming charged particles cannot travel directly to the lower atmosphere. The magnetosphere redirects many of them around the planet or traps them in regions of near-Earth space. Entry is easier near the magnetic poles where field lines connect more directly with the upper atmosphere. Energetic particles can move along these lines and reach high-altitude gases, creating additional ionization and increasing radiation exposure in polar regions. The atmosphere supplies a second protective layer. When high-energy particles collide with atoms of molecules, they lose energy and produce cascades of secondary particles. Most of this activity occurs high above the surface. At ordinary aviation, altitude's exposure can increase during a strong solar particle event, especially on polar routes where magnetic shielding is weaker. Airlines and space weather services monitor these conditions, and operations may be adjusted if the particle intensity becomes unusually high. Astronauts outside Earth's dense atmosphere face greater
Driven
concerns.
by immense gravity,
Spacecraft
the slow
shielding
rotation
reduces
sculpts matter into
exposure,
these
but
complex
cannot
galactic
block
structures.
every energetic proton without becoming extremely heavy. Missions in low Earth orbit receive some protection from the magnetosphere, while journeys beyond it would face a more direct particle environment. During elevated solar activity, crews can move to more shielded parts of a spacecraft and postpone work outside. Radiation monitoring remains essential because biological effects
Interstellar hydrogen can become luminous around energetic stars.
And the duration of exposure. Particle storms also affect technology. Energetic protons can penetrate spacecraft materials and disturb electronics. They can create false signals in detectors, alter memory states, and gradually damage solar cells. In the upper atmosphere, additional ionization can disrupt radio communication at high latitudes. Satellite navigation may become less reliable where signals pass through strongly disturbed polar regions. These effects differ from the day-side radio blackout produced by flare X-rays because particle disturbances can continue for many hours and can affect areas that are not directly sunlit. The timing and strength of a particle event remain difficult to predict precisely. Observations of a flare, a coronal mass ejection and a shock can indicate increased risk, but magnetic geometry controls whether the particles reach Earth efficiently. An eruption from the western side of the visible sun often connects more readily with the spiral magnetic field leading toward Earth, though real conditions can vary. Forecasts therefore combine solar images, radio measurements, particle detectors, and models of the solar wind. As the event develops, particle intensity can rise, remain elevated, and then decline slowly. Lower energy particles may arrive later and persist longer because they scatter more strongly. The surrounding magnetic field continues to shape their motion long after the flare's light has faded. Near Earth, the result is a layered disturbance made of different species energies and arrival times. These particles remain distinct from the flare's first radiation, yet they belong to the same active solar environment and reveal how magnetic energy can be carried outward through space. Their measurements allow researchers to follow the disturbance beyond its first bright moment, tracing how released energy continues moving through the magnetic space that surrounds the planet and nearby spacecraft. Beyond the first arrival of radiation and energetic particles, a slower disturbance may move outward from the Sun as a coronal mass ejection. A coronal mass ejection is a vast release of magnetized plasma from the solar atmosphere. It can accompany a strong flare, but the two events are not identical. The flare is a rapid release of electromagnetic energy, while the coronal mass ejection is a moving structure made of charged matter and magnetic field. One can occur without the other, and their strength does not always rise in the same proportion. When an eruption begins, part of the Sun's outer atmosphere can lift away from the surface. The material expands quickly because the pressure inside the disturbed magnetic structure exceeds the resistance of the
Ordinary water
surrounding
contains
corona.
neutron-bearing
At
oxygen
first,
nuclei,
the ejection
even though no
remains
free
close
neutrons
to
are
the
visible.
Sun, where magnetic fields are strong and the plasma is dense compared with interplanetary space. As it moves farther outward, the structure grows larger, its density decreases, and its magnetic field spreads across a wider volume. The ejection can eventually become wider than the Sun itself. Its path is shaped by several forces. The original direction depends on the location and magnetic structure of the active region. Nearby, coronal holes, streamers, and large magnetic fields can push or guide the ejection away from a simple, straight path. A structure launched near the center of the visible solar disk may appear likely to travel toward Earth, yet small deflections
Frozen
can change the
volatiles and
final
rocky
result.
grains hold neutrons
An eruption
bound within
near the
ordinary
solar
molecules
edge
and minerals.
may seem directed sideways, though a broad ejection can still extend into the Sun-Earth line. Solar
These
observatories
countless fragments of
use
ice and rock
coronagraphs
demonstrate
to
how
follow this
neutron-bearing
motion.
matter can
A
be distributed
coronagraph
across
blocks
many
the
small
bright
solid
solar
bodies.
disk, so that faint plasma in the surrounding corona becomes visible. In these images, a coronal mass
Crust,
ejection often
mantle-derived
appears
lava, and
as an
metallic interior
expanding
material
arc
all
cloud
contain
or
hidden
halo.
neutrons within stable matter.
A full halo seems
The
to
newly
surround
formed planetary
the hidden
rock
sun
contains
from the
neutron-bearing
observer's
heavy
viewpoint
elements.
and can indicate motion toward or away from the spacecraft. Geometry alone does not determine direction, so measurements from other positions help reveal the true shape and speed. Once the ejection
Living
enters
tissue,
into planetary
water,
space,
soil,
it moves
and
through the
stone
solar
all
wind
quietly contain
rather than
bound
through
neutrons.
emptiness. The solar wind already flows outward, carrying plasma and magnetic field from the sun. A fast coronal mass ejection can overtake this slower background flow and compress it.
Planetary history is
leading
recorded
edge
in
may
matter
drive a
whose
shock,
heavier
much
atomic
like a
nuclei
moving
contain
disturbance
bound
that
neutrons.
piles material ahead of itself. This shock can accelerate particles and alter the magnetic environment well before the central part of the ejection arrives. The speed of a coronal mass ejection varies widely. A slow event may travel at only a few hundred kilometers per second, while a very fast one can exceed 2,000 kilometers per second. Near the Sun, its speed does not remain constant. A fast ejection usually slows as it transfers momentum to the surrounding solar wind, while a slow ejection may be carried outward and gradually approach the background wind speed. Models use observed speed with
Immense
direction
stores
and
of
solar
hidden
wind
neutrons.
conditions to estimate arrival time near Earth. The journey commonly lasts from roughly 1 day to several days. Forecast uncertainty grows because the structure expands, changes shape, and interacts with the variable solar wind. Other eruptions may also be moving through the same region. A later, faster ejection can catch an earlier, slower one, producing a merged disturbance that is more difficult to predict. Even with detailed observations, the exact arrival time and magnetic orientation near Earth may remain uncertain until the structure approaches monitoring spacecraft. A direct arrival requires more than a powerful flare. The
Early
ejection
helium
must
already
travel along a
contains
path
neutrons,
that intersects
while ordinary
Earth's
hydrogen
orbit
does
at
not.
the correct time. If it passes north, southeast, or west of the planet, its effects may be weak or absent. A glancing encounter can disturb the outer magnetosphere without producing the full impact of a central strike. This is why the size of the flare alone cannot determine whether a geomagnetic storm will follow. Near Earth, spacecraft positioned upstream in the solar wind measure the approaching disturbance before it reaches the magnetosphere. They record changes in speed density, temperature, and magnetic field. The leading shock may cause a sudden rise in these values. Behind it, compressed solar wind can remain turbulent. The central magnetic structure may show a smoother rotation of field direction, lower temperature, and unusual magnetic strength. These measurements provide a brief warning before the disturbance reaches Earth. The magnetic direction inside the ejection is especially important. Earth's field points northward over much of the dayside boundary. When the incoming magnetic field also points northward, the two fields tend to remain more separated. When the incoming field turns southward, it can connect efficiently with Earth's field and transfer energy into the magnetosphere. A relatively modest ejection with a sustained southward field can therefore produce a stronger geomagnetic response than a faster event with an unfavorable orientation. The coronal mass ejection remains a broad evolving structure rather than a compact projectile. Its outer layers interact continuously with the solar wind, and its internal field can twist, weaken, or become distorted. By the time it reaches Earth's orbit, it may cover millions of kilometers. Earth occupies only a small part of that volume. The planet's response depends on which portion passes across the magnetosphere and how long the magnetic connection remains effective. Throughout the crossing, remote images and numerical models refine forecasts while uncertainty remains, because no instrument samples the entire expanding structure directly at once. Along this slower path, the solar eruption changes from a bright event near the Sun into a moving disturbance within interplanetary space. Its plasma expands, its magnetic field stretches, and its shock reshapes the solar wind ahead. The journey carries the possibility of a geomagnetic storm, but not a certainty. Direction, speed, width, interaction, and magnetic orientation all determine whether the released solar material reaches Earth and how strongly the planet responds. Around the path of every solar eruption lies the solar wind, a continuous outward flow of plasma released from the Sun's upper atmosphere. This flow fills the space between the planets and creates the background through which radiation, energetic particles, and coronal mass ejections must travel. It is not a steady breeze with one constant speed. Its density, temperature, magnetic field, and motion change from place to place and from hour to hour. Near Earth, the solar wind is usually thin, containing only a few particles in each cubic centimeter, yet its influence extends across the entire planetary system. The solar wind begins in the hot corona, where particles gain enough energy to escape the Sun's gravity. Electrons and protons dominate the flow, while helium nuclei and small amounts of heavier ions travel with them. Because these particles carry electric charge, their behavior is controlled not only by motion and pressure, but also by magnetic fields. The expanding plasma drags part of the Sun's magnetic field outward, producing an interplanetary magnetic field that reaches far beyond Earth's orbit. The Sun rotates while the solar wind moves away. This rotation causes the magnetic field to form a broad spiral pattern similar to a curve drawn outward from a turning source. The structure is known as the Parker spiral. It does not mean that particles follow a rigid wire through space. Instead, it describes the average direction of the magnetic field embedded in the flowing plasma. Charged particles tend to spiral around these field lines, while waves and irregularities can scatter them across nearby
Collapsing
parts.
clouds in space
Different
can
parts of the
divide,
Sun release
eventually
solar
forming
wind at
multiple
different
stars
speeds.
within the same
Fast
disk.
streams often emerge from coronal holes, which are regions where magnetic field lines extend openly into space. Slow wind is commonly associated with more complex boundaries near streamers and closed magnetic structures. A fast stream can catch slower wind ahead of it, compressing plasma and magnetic field into a broad interaction region. These structures rotate with the Sun and can pass Earth repeatedly while their solar source remains present. The background wind matters because a coronal mass ejection does not move through uniform surroundings. If the wind ahead is slow and dense, the ejection may lose speed more quickly. If the surrounding flow is fast, the relative difference may be smaller. The magnetic field can also guide energetic particles and influence the way an ejection expands. Models of arrival time, therefore, require more than the initial speed measured near the Sun. They also require an estimate of the changing medium across the full distance to Earth. Small disturbances are always present within the solar wind. Magnetic fluctuations, pressure
Within the
changes,
bright,
waves,
swirling
and
core,
turbulent
neutron-bearing helium
motion
is
create
continuously
an
manufactured,
irregular
powering the
environment.
star's intense
These
luminosity.
variations scatter energetic particles and make their arrival less direct. Some particles move rapidly along magnetic field lines, while others are delayed by repeated changes in direction.
As the core temperature
Turbulence
increases,
also affects
massive
how
stars
energy
fuse
is
hydrogen more
transferred
rapidly
the
through
plasma,
different dominant
gradually
reaction
heating
pathways.
particles, even as the wind expands into colder and more distant regions of the solar system. Near Earth, the solar wind usually travels at several hundred kilometers per second. Its density is so low that it would feel almost empty to ordinary matter, yet its speed and magnetic field allow it to transfer energy to the magnetosphere. The pressure of the flow compresses Earth's magnetic field on the day side and stretches it into a long tail on the night side. When the solar wind changes, the size and shape of this magnetic cavity change with it. The direction of the interplanetary magnetic field is especially important at the boundary of Earth's magnetosphere. When it turns southward for a sustained period, it can connect more effectively with the planet's northward field on the day side. This process allows solar wind energy to enter the magnetosphere. Even without a large coronal mass ejection, a fast stream with a suitable magnetic direction can produce geomagnetic activity. The surrounding wind is therefore an active driver rather than a passive background. Measurements of the solar wind come from spacecraft placed where they can sample the flow before it reaches Earth. These observatories record particle speed, density, temperature, and magnetic direction. Their position gives forecasters a short interval between detection and impact at the magnetosphere. The warning may range from tens of minutes
Deep within the
to
star,
about an
the
hour,
carbon burning
depending
phase
on
begins.
solar wind
Notice how
speed
each successive
and
fusion stage is shorter and far more concentrated at the center.
This interval helps operators prepare for possible changes in satellites' power systems and radio conditions. The solar wind also carries traces of the Sun's composition. Instruments measure the relative amounts and charge states of different ions. These properties reveal the temperature and magnetic environment where the plasma originated. Fast wind from coronal holes often has a different composition from slow wind released near streamer boundaries.
Iron-rich nuclei contain many neutrons and represent the endpoint of ordinary energy-releasing fusion.
With regions observed remotely on the solar surface and in the corona. As the Sun rotates, Earth passes through changing sectors of magnetic polarity. In one sector, the interplanetary field points generally away from the Sun, while in another, it points points generally toward it. The boundary between sectors can be broad and wavy. Crossing this boundary changes the local magnetic environment even when solar wind speed remains similar. Large eruptions move through this organized yet variable pattern and may become distorted as different parts encounter different conditions. The solar wind extends well beyond the planets until it meets the surrounding material between stars. Within Earth's orbit, however, it remains closely tied to daily
Fusion
space
can no
weather. It
longer
carries
release
magnetic
useful energy from the
structure,
growing iron core,
guides particles,
sealing the
shapes
star's fate.
the magnetosphere, and controls the medium through which solar eruptions move. Around the recent flare, it forms the broad, moving environment that determines how later disturbances spread, slow connect, and finally reach the region surrounding Earth. Its quiet presence links the Sun to every planetary orbit, carrying ordinary conditions and sudden disturbances alike, while remaining nearly invisible, except through instruments that detect the particles, fields, pressures and motions passing continuously through surrounding space. Closer to the Sun, the solar wind can be traced back into the outer corona, the broad and luminous atmosphere that surrounds the visible solar disk. The corona extends millions of kilometers into space and becomes gradually thinner with distance. It has no hard outer edge. Instead, its plasma expands until it merges with the continuous solar wind. During a major eruption, this region provides the immediate environment through which hot material, magnetic fields, shocks and waves begin moving away from the Sun. The outer corona is far less dense than the layers below it, yet its temperature reaches more than 1 million degrees Celsius in many regions. This high temperature does not make it bright in ordinary visible light because the particles remain widely separated. During a total solar eclipse, the corona appears as a pale glow surrounding the darkened Sun. Spacecraft observe it more regularly with coronagraphs, which block the intense light of the solar disk and reveal faint structures beyond the edge. The shape of the outer corona changes with solar activity. Near solar minimum, it often appears relatively ordered, with long streamers extending near the Sun's equatorial regions and open magnetic fields emerging from broad polar coronal holes. Near solar maximum, the structure becomes more complex. Streamers, loops, holes, and active regions appear at many latitudes. Magnetic fields twist and connect across a less symmetrical atmosphere. This complexity creates more opportunities for eruptions to disturb wide regions of the corona. Plasma in the outer corona is closely tied to magnetic fields. Because it is electrically charged and highly conductive, it tends to move with the field while also changing the field through its own motion. In closed structures, magnetic lines arch back toward the solar surface containing hot plasma within loops and streamers. In open structures, field lines extend outward into space, allowing plasma to escape more easily. The boundary between closed and open regions shifts as magnetic pressure, gas pressure, and large-scale solar motion change. A major flare alters this environment even when the brightest emission comes from lower regions. Energy released near an active region heats plasma and disturbs the surrounding magnetic structure. Waves move outward through the corona, compressing and rarefying the charged gas. Some disturbances appear as expanding fronts in extreme ultraviolet images. These fronts can travel across large portions of the solar atmosphere, changing speed as they encounter different magnetic fields and plasma densities. When a coronal mass ejection is present, the outer corona becomes the first region where its full expansion can be followed. The eruption may begin as a rising loop, a swelling cavity, or a lifting filament of cooler, dense material. As it moves higher, the structure pushes surrounding plasma aside. A bright, leading edge can form where material is compressed. Behind it, a darker cavity may reveal the magnetic body of the eruption. Dense material from lower in the atmosphere can remain embedded within the expanding form. The eruption does not move through the corona without resistance. The surrounding plasma and magnetic field exert pressure against it. A fast ejection can drive a shock when its speed exceeds the local speed at which magnetic disturbances travel through the plasma. This local limit changes across the corona because density and magnetic strength both vary. The shock may form close to the Sun or farther outward, depending on the eruption's acceleration and the environment through which it passes. Radio observations provide another way to follow this process. Electrons accelerated near shocks can produce radio emissions that drift toward lower frequencies as the disturbance moves into regions of decreasing density. These emissions help estimate the motion of the shock even when direct images are incomplete. Combined with coronagraph observations, they reveal how the eruption expands through the outer atmosphere and begins entering interplanetary space. The outer corona also contains long helmet streamers, named for their curved shapes above closed magnetic regions. These streamers can bend, swell, and release blobs of plasma into the solar wind. A large eruption may disrupt an entire streamer, opening magnetic structures that later reconnect behind the departing material. The corona then begins to reorganize. Bright rays may form in the wake of the ejection, marking extended sheets where magnetic fields are drawn together and rearranged. Coronal holes form another important part of the surrounding environment. They appear dark in extreme ultraviolet images because their plasma is cooler and less dense than nearby regions. Their open magnetic fields allow fast solar wind to flow outward. A coronal hole beside an active region can influence the direction of an eruption by applying uneven magnetic pressure. The expanding structure may be deflected away from the hole and toward regions where the surrounding field offers less resistance. Observations of the outer corona remain challenging because its visible light is faint compared with the solar surface. Instruments must suppress scattered light and maintain stable measurements across a large range of brightness. Multiple spacecraft provide different viewing angles, allowing scientists to estimate the three-dimensional form of an eruption more accurately. Even so, some features overlap along the line of sight, and the true shape may remain uncertain. Within this extended atmosphere, the recent flare belongs to a larger magnetic disturbance. Hot plasma brightens broad fronts, travel outward, streamers bend, and any associated ejection expands through decreasing density. The outer corona transforms concentrated activity near one solar region into a disturbance capable of spreading across a vast volume. Its structures guide, resist, and reshape the escaping material while feeding the solar wind that fills the space between planets. Across this region, expansion remains continuous. At this level, the Sun is no longer only a bright sphere with a visible edge. It becomes the center of a flowing atmosphere held and shaped by magnetism, heated to extreme temperatures and open to space through countless changing paths. The flare's influence passes through this atmosphere as light, motion, compression, and magnetic change, leaving the outer corona briefly altered before its plasma continues its outward expansion. Above the active region, the corona is shaped by magnetic loops that rise from the solar surface and curve back down again. These loops are not solid arches, they are paths traced by hot plasma moving within magnetic fields. Because the plasma is electrically charged, its motion is guided along the field. In extreme ultraviolet and X-ray images, the loops appear as bright curved structures, sometimes compact, sometimes broad. Their changing form reveals where magnetic energy is stored, released, and redistributed during a major flare. Each loop begins where magnetic field lines emerge from one area of the photosphere and return through another. These two ends are called foot points. They are rooted in regions of opposite magnetic polarity, often near sunspots. The field between them arches through the corona where gas pressure is low and magnetic forces dominate. Plasma collects along these paths, and its brightness depends on temperature density and the wavelengths observed. A loop that appears bright in one instrument may look faint in another because each instrument is sensitive to a different range of plasma conditions. Before a flare, many loops above an active region may already show signs of stress. Their field lines can be stretched, sheared, or twisted by motions below. The visible loops do not reveal every field line, but they provide a partial map of the larger magnetic structure. Some lie low and close to the surface, while others rise higher. Several systems can overlap, forming a complex arrangement in which neighboring loops point in different directions or press against one another. This complexity allows magnetic energy to accumulate over time. During the flare, some coronal loops brighten suddenly. Energy released in the magnetic field accelerates. Particles and heats plasma to many millions of degrees Celsius. Particles travel along field lines toward the lower atmosphere, where they deposit energy near the foot points. Heated material then expands upward into the loops. This process, called chromospheric evaporation, fills the magnetic arches with dense hot plasma. The term describes upward motion from lower solar layers rather than the gentle evaporation of liquid water. As the plasma enters the loop X-ray and extreme ultraviolet emission increase, the brightest loops often appear after the initial energy release. They form a growing system known as a post-flare arcade, a series of neighboring arches spanning the active region. The word arcade describes their repeated curved shape. These loops are created as magnetic fields reconnect above them and settle into shorter, less stressed configurations. Newly formed loops appear higher with time because reconnection continues in regions farther above the surface. The arcade can therefore seem to rise, although individual loops remain anchored at their foot points and gradually cool. Cooling occurs through several processes. Hot plasma loses energy by emitting radiation, and heat also travels along the magnetic field towards denser, lower layers. As the temperature falls, the same loop may become visible in different wavelengths at different times. It may first appear in high-energy X-rays, then in hotter,
breathable oxygen owes most of its atomic mass to protons and neutrons concentrated in the nucleus.
This sequence allows scientists to follow the changing thermal state of the plasma. Dense loops can remain visible long after the flare's sharp X-ray peak has ended. The shape of a loop also contains information about magnetic force. Smooth curved arches suggest plasma following a stable field, while rapid motion, contraction, or oscillation can indicate recent disturbance. Some loops appear to shrink after reconnection, moving downward as magnetic tension pulls them into a lower state. Others sway after nearby eruptions or waves pass through the corona. These oscillations act like natural probes. Their period and motion help estimate magnetic strength and plasma density within structures that cannot be touched directly. Not all bright arches are simple, isolated loops. Several strands may lie close together within one visible feature. Each strand can be heated at a different time, producing a braided or layered appearance. Instruments have limited resolution, so a smooth loop may contain finer structure below the scale of detection. Observations indicate that coronal heating often occurs in many small episodes rather than as one perfectly uniform release. It remains uncertain how much of the loop's internal structure is unresolved in every event. Magnetic loops confine plasma because charged particles find it easier to move along the field than across it. This confinement creates sharp boundaries between neighboring structures with different temperatures. A hot loop can lie beside cooler material without immediate mixing. The field acts as an organizing framework, separating the corona into narrow channels of plasma. When reconnection changes that framework, particles and heat gain access to new paths. The loop system then rearranges both its magnetic shape and its distribution of energy. In active region 4366, the large flare illuminates this magnetic architecture. Bright loops mark zones where plasma is heated and contained. Compact sources
even under extreme temperatures, these neutron-bearing nuclei remain perfectly stable within the crucible structure.
Reveal the paths connecting.
Advanced electronics are built around stable neutron-bearing nuclei.
As some structures brighten, others fade. Newly reconnected loops appear above These changes do not represent material moving freely through empty space. They show plasma responding to a magnetic framework that is itself being transformed. The loops remain part of the corona even when the flare becomes less intense. Their plasma continues to cool, drain,
Solar energy
and
conversion
settle.
rearranges only the
Material
electrons.
can flow downward.
The nuclei
along
and their
both
neutrons
legs under
remain
gravity,
completely
while
unchanged.
some remain suspended by pressure and magnetic confinement. The arcade gradually becomes less
Magnetic
bright
fields
as
arise mainly
density
from
and
charged
temperature
particles,
decline.
while neutrons remain
Small
hidden within the
motions
nuclei.
continue, and the surrounding field approaches a more stable arrangement. Within these curved structures, the flare becomes visible as an organized pattern rather than a single flash. Magnetic energy turns into particle motion, heat, and radiation. Plasma fills newly connected paths, outlines invisible fields, and slowly changes color across different instruments as it cools. The coronal loops preserve the geometry of the disturbance for hours, recording the flare's evolution in a sequence.
Primitive
of bright
solar system
arches
matter
above
carries
the
bound
active
neutrons
region.
within a
Beneath the
diverse
bright
mixture of
coronal
elements.
loops, the solar atmosphere narrows into a thin and rapidly changing layer. Known as the transition region, it lies between the relatively cool chromosphere and the much hotter corona, yet it is not a smooth boundary with one fixed height. Its position shifts with magnetic structure, local heating density, and time. In some places it stands higher above the visible surface, while in others it bends downward around active regions and magnetic loops. During a major flare, this already complex layer becomes strongly disturbed as energy moves through it in both upward and downward directions. The transition region contains plasma at temperatures ranging from tens of thousands to several 100,000 degrees Celsius. Across a comparatively small vertical distance, temperature rises sharply while density falls. This steep change makes the region scientifically important because it marks where the character of the solar atmosphere changes. Below it, collisions between particles remain frequent and neutral atoms are still present in meaningful amounts. Above it, the plasma is almost fully ionized. Magnetic forces dominate more strongly, and temperatures reach coronal values of more than 1 million degrees Celsius. The layer is observed mainly in ultraviolet and extreme ultraviolet wavelengths. Different ions emit light most strongly at particular temperatures, so instruments select narrow bands that reveal plasma in specific thermal conditions. Emission from carbon, oxygen, silicon, and other elements outlines small loops, bright knots, narrow ribbons, and rapidly changing threads. These features often look finer and more restless than the larger coronal arches above them. Their brightness changes when density rises, when temperature shifts, or when energy passes through the region. During the flare, energy released in the corona travels downward along magnetic field lines. Fast electrons, heat conduction, and waves all carry part of this energy toward denser layers. As they enter the transition region, they encounter more particles and more frequent collisions. Energy that moves easily through the thin corona begins to spread into the surrounding plasma. Electrons, slow ions, become more highly charged, and radiation increases. The transition region, therefore, acts as a narrow zone where coronal energy is redistributed before reaching the chromosphere below. The downward energy flow does not remain confined to one height, because temperature and density vary so sharply. Each part of the region responds differently. Hotter upper layers can conduct heat efficiently along magnetic fields. Cooler lower layers radiate energy more effectively because they contain more particles. The balance between heating, conduction, radiation, and motion determines the local structure. During a flare, this balance changes faster than under quiet
This proton
conditions,
trapping detector
causing
counts the decay
layer
events,
to brighten,
allowing us to
shift,
precisely
compress,
measure the
and
neutron
expand.
lifetime.
Pressure also rises when plasma is heated. The heated material expands both upward and downward, although the easier path often follows the magnetic field. Upward motion supplies hot, dense plasma to coronal loops, while downward motion can compress cooler layers. In ultraviolet spectra, these flows appear as small shifts in wavelength. Light from material moving toward an instrument shifts slightly in one direction, while light from material moving away shifts in the other. These measurements reveal velocities that cannot be seen directly in a single image. The transition region is not uniform across the active region. Above strong magnetic concentrations,
The gate opens, and the surviving ultra-cold neutrons stream toward the detector.
structures.
By counting these
Along
flashes,
loop
we can
footpoints,
infer
it
the neutron's
traces
lifetime.
narrow channels where energy enters the lower atmosphere. Between these zones, weaker magnetic fields and cooler plasma create darker areas. The pattern changes as reconnection redirects energy into new field lines. A location that is faint before the flare may brighten suddenly when newly accelerated particles reach it, while an earlier bright feature may fade as heating moves elsewhere. Radiation from this layer also carries information about density. Some ultraviolet emission lines change their relative strength when particles collide more often. By comparing these lines, scientists estimate how many electrons occupy a given volume. During flares, densities can rise sharply near loop footpoints as compressed and heated material fills the region. These estimates help explain how much energy is being deposited and how quickly plasma is moving upward into the corona. The transition region responds on short timescales because it is thin and because the incoming energy can be intense. Brightness may change within seconds. Small structures appear, merge, move, and vanish as magnetic connections evolve. Even after the main X-ray peak declines, the layer remains active, while coronal loops cool and conduct heat downward. Repeated energy release can produce repeated brightenings at the same or neighboring locations. Its extreme temperature gradient remains one of the central problems of solar physics. The corona above is far hotter than the photosphere below, even though the visible surface is closer to the sun's interior energy source. Observations indicate that magnetic processes transport and release energy in the outer atmosphere, but the detailed contribution of waves, small reconnection events, and turbulent motion remains under study. The transition region records the effects of these processes because nearly every exchange between the chromosphere and corona passes through it. Its emissions also help separate the timing of particle impacts from slower conductive heating. When several ultraviolet channels brighten in sequence, their order reveals how temperature changes through the layer, while simultaneous brightenings can indicate a sudden, strong, distributed energy input. During the X-class flare, the layer becomes a narrow but essential part of the energy pathway. It receives heat, and particles from above radiates strongly in ultraviolet light and channels heated plasma upward. Its location shifts as pressure changes and its small magnetic structures brighten beneath the larger coronal loops. Though it occupies only a limited vertical range, it connects two atmospheric regions with very different temperatures, densities, and physical behavior. Within this changing boundary, the flare is transformed from coronal magnetic energy into local heating, radiation, and mass motion. The transition region does not merely separate the corona from the chromosphere. It regulates the exchange between them, responding quickly to every new pulse of energy and preserving that response in fine ultraviolet structures along
driven
the
by immense
active
gravity.
region.
The
Beneath
slow
the
rotation
transition
sculpts
region,
matter
the
into these
chromosphere
complex
forms
galactic
a thicker
structures.
and cooler layer of the solar atmosphere. It lies above the photosphere and extends upward through plasma that changes in density, temperature, and ionization. During quiet conditions, the chromosphere appears mottled and threaded by narrow structures shaped by magnetic fields. During a major flare, selected parts brighten intensely. These bright areas often
Interstellar
form
hydrogen
long
can become
separated
luminous
bands
around
called
energetic
flare
stars.
ribbons. Each ribbon marks the lower end of magnetic field lines involved in the energy release above. Flare ribbons do not represent solid lines painted across the solar surface. They are regions where heating becomes concentrated in the lower atmosphere. Their shapes follow the magnetic pattern of the active region, lying on opposite sides of a magnetic boundary. One ribbon forms over positive magnetic polarity, while another forms over negative polarity. Together, they outline the footpoints of coronal loops that reconnect higher above. As reconnection continues, new field lines connect to new locations, and the ribbons appear to spread apart across the chromosphere. The motion of the ribbons does not mean that the entire magnetic structure slides across the surface at the same speed. Instead, it records the progressive involvement of neighboring field lines. Each newly reconnected line carries energy downward toward a fresh pair of footpoints. Those locations brighten, while earlier locations begin to cool. The changing pattern allows scientists to trace how the reconnection region grows through the magnetic system. Ribbon speed, brightness, and magnetic strength together provide estimates of how rapidly magnetic flux is being processed during the flare. Energy reaches the chromosphere through several channels. Accelerated electrons travel along magnetic field lines and collide with denser particles below. These collisions slow the electrons and convert their directed energy into heat ionization, excitation, and radiation. Thermal conduction also carries energy downward from hot coronal plasma. Waves may contribute additional heating by transporting energy along the same magnetic paths. The relative importance of these channels can vary during different phases of the flare, and observations do not always separate them completely. The chromosphere responds strongly because its density is higher than that of the corona. Incoming particles encounter frequent collisions and energy is deposited over a short distance. Atoms become excited, electrons are removed, and the local temperature rises. Radiation increases across visible ultraviolet and extreme ultraviolet wavelengths. Some emission comes from hydrogen, which is abundant throughout the solar atmosphere. Other emission comes from ionized metals whose spectral lines reveal temperature density and motion. One familiar chromospheric signal is hydrogen emission. During a flare, hydrogen atoms absorb energy and later release it at characteristic wavelengths. Images made in selected hydrogen light show ribbons, kernels, and fine threads crossing the active region. Compact kernels are bright points within the larger
Ordinary
ribbon
water
system.
contains neutron-bearing oxygen nuclei, even though no free neutrons are visible.
Their rapid changes reveal that the heating is not perfectly smooth, but arrives in pulses across small magnetic strands. As the chromosphere heats, pressure increases, hot material expands upward along the magnetic field and fills coronal loops. This upward flow supplies the dense plasma later seen in X-rays. At the same time, part of the atmosphere can be pushed downward. Spectral measurements show upward and downward motions occurring close together, separated by temperature and height. The upward component becomes hotter and faster, while denser, cooler material below may move downward more slowly. These paired motions form a direct response to sudden energy deposition. The ribbons can lengthen as well as separate. Reconnection may begin in one portion of the active region and extend along the magnetic boundary. Brightening then travels along the ribbon, linking compact kernels into a continuous form.
These countless fragments of ice and rock demonstrate how neutron-bearing matter can be distributed across many small solid bodies.
And how it spreads. Some segments brighten repeatedly when multiple bursts of energy reach the same area.
Crust, mantle-derived lava, and metallic interior material all contain hidden neutrons within stable matter.
Cooling. The chromosphere,
the newly formed planetary rock, contains neutron-bearing heavy elements.
Density allows frequent particle interactions. So much of the deposited flare energy is released as light. This radiation spans wavelengths and can exceed the coronal radiation in total energy.
Living tissue, water, soil, and stone all quietly contain bound neutrons.
The lower atmosphere, therefore, plays a major role in the flare's energy budget. It receives energy from above, converts it into heat and motion, and sends a large fraction back into space as radiation.
Planetary history is recorded in matter whose heavier atomic nuclei contain bound neutrons.
This brightening occurs in or near the deepest atmospheric layers reached by flare energy. Its exact formation can involve several processes, including direct heating changes in ionization and radiation from higher layers that warms denser material below. Observations indicate that the strongest white light sources often coincide with intense ribbon kernels. It remains uncertain how the different heating mechanisms divide their contributions in every event. The chromosphere is highly structured before the flare begins. Thin jets, fibrils, and spicules rise and fall along magnetic
stores
fields.
Of hidden neutrons.
Strong flare heating temporarily overwhelms parts of this ordinary pattern. Ribbons become the dominant visible structures while nearby regions remain comparatively quiet. The contrast reveals how narrowly the magnetic field channels energy. Two areas separated by a short distance can experience different heating because they connect to different coronal paths. As the X-class event progresses, the ribbon system maps the changing magnetic connections above active region 4366. Bright bands appear at opposite polarities, compact kernels pulse within them, and heated plasma rises into newly formed loops.
Early helium already contains
neutrons, gradually
while
fade
ordinary
as
hydrogen
particle
does
impacts weaken and the atmosphere cools. Recombination reduces ionization, radiation declines, and ordinary chromospheric structure begins to return. Within this lower atmospheric layer, the flare becomes concentrated into narrow patterns of light. The ribbons show precisely where magnetic energy reaches dense plasma, where particles lose their energy, and where hot material begins its upward motion. Their slow expansion across the active region records the continuing rearrangement of magnetic fields above, while their brightness preserves the intense but temporary heating of the chromosphere. The photosphere forms the bright visible surface of the Sun, although it is not a solid boundary. It is a layer of glowing gas, several hundred kilometers thick, where rising energy finally escapes freely enough to travel into space as visible light. Below it, the solar interior is too dense for light to move directly. Above it, the atmosphere becomes thinner and more transparent. Most ordinary images of the Sun show this layer, including the dark sunspots, bright magnetic patches, and fine grain-like pattern that surrounds active region 4366. The photosphere has an average temperature near 5,800 degrees Celsius. Its light comes from plasma that remains dense enough to absorb and emit radiation efficiently. The apparent surface marks the height where visible photons can leave without being repeatedly absorbed. Looking toward the center of the solar disk reveals somewhat deeper and hotter material than looking near the edge. This produces limb darkening, a gradual reduction in brightness toward the Sun's visible boundary. The effect helps reveal how temperature changes through the photospheric layer. Across the quiet photosphere, convection creates a pattern called granulation. Each granule is a bright cell of rising hot plasma, surrounded by darker lanes where cooler plasma sinks. A typical granule spans about 1,000 kilometers and lasts for several minutes before changing shape. Larger flows also move beneath and across the surface. These motions carry heat upward and continuously push magnetic fields, gathering them into narrow regions between convective cells. In active areas, magnetic forces become strong enough to alter the ordinary pattern. Sunspots appear dark because powerful magnetic fields suppress part of the upward convective flow. With less hot plasma reaching the surface, a sunspot becomes cooler than its surroundings. It still emits intense light, but the brighter photosphere beside it makes it appear nearly black in ordinary images. A mature sunspot often contains a dark central umbra surrounded by a lighter penumbra. The penumbra is formed from elongated filaments arranged around the center, tracing inclined magnetic fields and organized plasma motion. Active Region 4, 366 contains a large collection of sunspots rather than one isolated dark mark. The group emerges as magnetic flux rises through the photosphere from below. Positive polarity appears where the magnetic field points outward, while negative polarity appears where it returns inward. Instruments called magnetographs measure these directions through small changes in spectral lines. Maps of the region show strong fields packed closely together, with opposite polarities separated by complex boundaries. The numbering of an active region is an operational label used to follow it across the solar disk. It does not describe its physical strength or age. A region receives a number after observers identify a significant sunspot group, and the label allows forecasts, measurements, and reports to refer to the same source. As the sun rotates, the region moves across the visible hemisphere from east to west. Its changing position affects how clearly its magnetic structure can be measured and how directly its radiation reaches Earth. The photospheric magnetic arrangement provides an important measure of flare potential. A simple region may contain one positive area and one negative area with a broad
Collapsing
separation.
clouds in space can divide,
A complex
eventually
region
forming
can
multiple
contain
stars
many
within the same
fragments,
disk.
Sharp polarity boundaries and strong fields pressed close together. Active Region 4, 366 develops this greater complexity. Its sunspots contain mixed and crowded magnetic polarities, creating conditions in which the overlying field can store substantial energy. The photosphere itself does not release the flare's full energy, but it anchors the magnetic structures that do. Near the strongest polarity boundary, motions continue after the region emerges. Sunspots may rotate slowly. Smaller magnetic elements drift, divide, merge, or slide past one another. Convection pushes against the field while the field resists and redirects the flow. These movements change the arrangement of the magnetic footpoints. Because the overlying field remains attached to them, photospheric motion can shear and twist the coronal structure gradually. The stored energy increases when the field departs from a simpler, lower energy shape. Observers follow these changes with visible light images and magnetic maps. High-resolution images
Within the bright,
reveal
swirling
dark
core,
umbrae,
neutron-bearing helium is
filamented
continuously
penumbra,
manufactured,
bright
powering the
points
star's
and
intense
narrow
luminosity.
light bridges crossing some spots. Magnetic measurements show field strength and direction across the same structures. Sequences taken over hours reveal growth, decay, rotation, and fresh emergence.
As the core temperature increases, massive
4,
stars fuse hydrogen more rapidly through different dominant reaction pathways.
Strong flares. because its surface pattern remains magnetically complicated even after individual releases. A major flare can also leave subtle changes in the photosphere. Magnetic measurements sometimes show rapid and lasting shifts near the polarity boundary. Penumbral filaments may alter brightness and small surface flows may change. These effects suggest that the coronal field's sudden rearrangement applies forces back toward the dense lower atmosphere. The photosphere moves far more slowly than the thin corona, yet it remains physically connected to the event through the same magnetic system. Bright flare emission can briefly appear against the photospheric background during the strongest events. These white light sources are usually compact and lie near intense ribbon kernels. They do not cover the entire sunspot group. Their formation reflects concentrated energy reaching deep layers where increased radiation becomes visible beside the ordinary solar continuum. After the brief brightening fades, the sunspots remain still marking the magnetic roots of the active region. At the visible surface, active region 4366 therefore appears as a changing landscape of dark spots, bright granules, magnetic fragments, and crowded polarity boundaries. Its structure records the emergence and motion of magnetic flux from below. The photosphere anchors the loops above channels, the pattern of flare ribbons, and
deep within the star, the carbon burning phase begins. Notice how each successive fusion stage is shorter and far more concentrated at the center.
The flare's source is expressed not as open fire, but as a dense magnetic arrangement embedded within the sun's continuously moving surface. Its continuing evolution shows why one powerful release can occur while enough magnetic complexity remains for additional activity within the same numbered region during following days of observation. Beneath the visible surface, the magnetic structure of active region 4366 continues downward into the convective layers
Iron-rich
of the
nuclei
sun.
contain many neutrons and represent the endpoint of ordinary energy-releasing fusion.
Below it, hot plasma rises, cooler plasma sinks, and electrical currents move through a turbulent environment. Magnetic fields are carried, stretched, twisted, and compressed by these motions. Sunspots appear where strong bundles of magnetic flux reach the surface and reduce the normal upward transport of heat. The convective zone occupies the portion of the solar interior. In this region, energy is carried mainly by moving plasma rather than by radiation alone. Hot material rises because it is less dense, while cooler material descends after releasing energy near the surface. These motions occur across many scales. Small cells contribute to granulation, while larger flows extend far below the photosphere.
Fusion can no longer release useful energy from the growing iron core,
Together,
sealing
they
the
create
star's
a
fate.
constantly changing background that shapes the magnetic field. Magnetic flux does not behave like a rigid pipe beneath a sunspot. It forms a structured concentration that interacts with surrounding plasma. Some parts remain strongly connected, while others spread, divide, or reconnect on smaller scales. The field resists being bent, but the moving plasma also exerts pressure. The resulting balance determines whether a magnetic concentration rises, remains trapped, or becomes distorted before reaching the surface. As magnetic flux rises, pressure around it decreases. The expanding bundle becomes wider and more complex. Buoyancy helps lift it because magnetic pressure replaces part of the gas pressure inside the structure, making the region less dense than its surroundings. The ascent is slow compared with the rapid release of energy during a flare. It may take days or longer for a large magnetic system to move through the upper convective zone and form a visible active region. The rising field is influenced by the sun's rotation. Rotating plasma tends to curve and twist moving structures. This effect contributes to the preferred orientation of active regions in each solar hemisphere. It also helps produce a systematic tilt between the leading and following sunspots of a magnetic pair. The pattern is not identical in every region because turbulence and local flows introduce variation. Active Region 4 3666 develops within this rotating and convecting environment. Fresh magnetic flux can continue to emerge after the first sunspots appear. New fragments rise between older spots, increasing the amount of field near the surface. When the direction of new flux differs from the existing arrangement, strong gradients form along polarity boundaries. The overlying field then becomes more crowded and less able to relax into a simple shape. Continued emergence is one reason an active region can remain capable of major flares after an earlier release. Subsurface flows also move the anchored ends of magnetic structures. Horizontal motion can push opposite polarities closer together or slide them past one another. Rotational motion beneath a sunspot can turn the field around its central axis. These movements inject stress into the magnetic atmosphere above. The energy is stored gradually because the dense layers below move slowly, while the coronal field responds through tension and electric currents. Scientists study these hidden layers through helioseismology, a method that examines waves traveling through the sun. The surface rises and falls in patterns produced by sound waves moving through the interior. Their speed and path depend on temperature, density, motion, and magnetic fields. By measuring small changes in these waves, researchers estimate flows beneath active regions. The method resembles medical imaging in principle, although the sun's turbulence and magnetism make interpretation difficult. Observations indicate that large active regions are associated with complex subsurface motion. Some measurements show converging flows near sunspots, while others reveal deeper patterns that differ with depth and stage of development. Strong magnetic fields also alter the waves directly, making it difficult to separate true plasma motion from magnetic effects. It remains uncertain how precisely the full three-dimensional structure can be reconstructed beneath every active region. The base of the convective zone lies far below the photosphere, where rotating layers move at different speeds. This broad shear region contributes to the solar dynamo, the process that generates and maintains the sun's global magnetic field. Large-scale fields formed there or distributed through the convective zone can be carried upward and reorganized by turbulence. The exact depth at which individual active region fields are assembled remains an area of research. Within the upper convective layers, magnetic fields can gather into stronger concentrations as surrounding flows push weaker field aside. Downflow lanes help collect flux, while buoyant sections rise toward the surface. A single active region may therefore contain field that has followed several paths and emerged at different times. This produces the fragmented and evolving pattern seen in magnetic maps of the photosphere. Sunspots remain stable only while magnetic forces are strong enough to resist disruptive convection. Around their edges, hot plasma continues to press inward. Some energy travels through narrow channels, producing bright structures within the penumbra. Beneath the umbra, convection is reduced, but not completely absent. Motions become organized by the strong vertical field, allowing limited transport, while maintaining the cooler dark appearance above. After a major flare, the deep magnetic roots do not suddenly vanish. The flare rearranges part of the field in the atmosphere, but the active region remains anchored within dense plasma below. Subsurface motion continues. Fresh flux may still rise, and existing footpoints keep moving. The amount of remaining stored energy depends on the full magnetic structure, much of which cannot be observed directly. Beneath active region 4, 3-6, 6 slow convection and rotation continue to shape the field. Rising plasma carries magnetic flux upward, sinking plasma gathers and bends it, and broad flows move its anchored ends. These processes build the surface pattern over time and maintain the strong magnetic foundation of the sunspots. The visible region above is therefore the upper expression of a deeper, evolving system embedded within the outer interior of the Sun. At the deepest level reached in this account, the flare begins with magnetic energy stored in the active region. The field above and within the sunspots is not calm or simple. It is stretched by surface motion, twisted by rotation, compressed by emerging flux, and crowded along boundaries where opposite polarities lie close together. This stressed configuration contains free magnetic energy, meaning energy above the amount required for a simpler and more relaxed field. The flare begins when part of this stored energy is released through magnetic reconnection. Magnetic reconnection is a process in which magnetic field lines change their connections within a thin region of strongly concentrated electric current. Field lines are useful descriptions of magnetic direction, not physical strings, yet their changing pattern reveals a real transfer of energy. In an ideal, highly conducting plasma field and plasma tend to move together. Near a narrow current sheet, however, conditions allow the magnetic pattern to break from that simple motion. Oppositely, directed fields approach, rearrange, and emerge in new connections. The current sheet forms where the field changes sharply across a small distance. Electric currents intensify there because charged particles respond to the steep magnetic difference. The sheet can become unstable and fragment into smaller structures. Reconnection may then occur in many linked sites rather than in one smooth location. These sites convert magnetic magnetic energy into heat bulk, motion waves, and accelerated particles. The rapid release becomes possible because the current sheet concentrates a large magnetic difference into a narrow region. As reconnection begins, newly connected field lines are sharply bent. Magnetic tension pulls them away from the reconnection site, much as a stretched elastic shape moves toward a straighter form. Plasma is carried with this motion, producing fast outflows in opposite directions. Above the active region, some reconnected fields join the outward eruption. Below it, others contract into closed loops. These downward loops fill with heated plasma and become the bright arcade observed after the strongest phase. Energy also reaches particles directly. Electric fields and turbulent magnetic structures accelerate electrons and ions to high speeds. Some particles remain trapped in the corona, where they collide with plasma and emit high-energy radiation. Others travel downward along magnetic fields toward the dense lower atmosphere. Their collisions heat the chromosphere, create strong radiation, and drive hot material upward into coronal loops. In this way, reconnection links the smallest current structures with the broad, bright pattern of the flare. The release does not necessarily occur all at once. Magnetic reconnection can begin in one location and spread through neighboring structures. Bursts of particle acceleration and radiation appear as different sections of the current sheet become active. The measured X-ray output rises when heating and particle production intensify, reaches a peak, and then declines as the rate of energy release weakens. Even during the decline, reconnection may continue at a lower level while loops keep forming and cooling. A major flare removes only part of the free magnetic energy stored in an active region. The remaining amount depends on the size and structure of the field involved. Some magnetic systems may relax substantially while nearby systems remain stressed. The same sunspot group can contain several separate zones of concentrated current. One eruption may disturb them without releasing all of their energy. The field can therefore remain capable of further flares after a powerful event. Continued emergence from below can rebuild stress. New magnetic flux enters the photosphere, pushes against older fields, and changes the polarity boundaries. Sunspot rotation and horizontal flows also continue. These slow motions supply energy to the magnetic atmosphere after the first flare has ended. The process does not guarantee another major eruption, but it preserves conditions in which further reconnection can become possible. Scientists estimate flare potential by examining magnetic complexity, recent activity, flux emergence, strong polarity gradients, and the motion of sunspots. These indicators show whether an active region remains energetic, but they do not provide an exact clock. The final trigger may involve changes too small, too high, or too poorly measured to identify in advance. Forecasts therefore describe the probability of additional flares over a period rather than predicting a precise minute. Repeated flares from one active region.
Breathable oxygen owes most of its atomic mass to protons and neutrons concentrated in the nucleus.
Field release less energy or produce a stronger peak. It may remain confined within closed loops or accompany another outward eruption. The X-ray class alone does not determine the full result. Duration, particle acceleration, location, coronal mass ejection, direction, and magnetic connection with Earth all shape the effects beyond the Sun. Within active region 4. 366. The persistence of strong magnetic fields and repeated activity indicates that the system does not become completely relaxed after one release. Observations can identify continuing complexity, while the precise sequence of later events remains uncertain. The phrase that the activity is not over describes this continuing potential rather than a certainty that another stronger flare must occur. The Sun's magnetic atmosphere remains capable of change, but each new release depends on evolving conditions. At the innermost mechanism of the event, the enormous flare reduces to the behavior of plasma and magnetic fields within narrow current structures. Stressed fields approach reconnection, changes their connections, tension drives rapid flows, and particles receive energy. The released energy spreads outward through loops, radiation waves, particles, and moving plasma. Some of the magnetic system settles while some remains stressed and anchored to continuing motion below. Continuous measurements follow these changes, comparing magnetic maps, ultraviolet images, X-ray emission radio signals, and particle data as the active region slowly evolves over time. The flare is therefore not a separate fire burning above the Sun. It is a rapid conversion of magnetic energy within an active and evolving plasma. Its strongest moment passes, but the region continues to rotate, convect, emerge, and reorganize. As long as substantial magnetic complexity remains, further releases are possible, though their timing and strength cannot be known with certainty. The active region continues its slow passage.
Even under extreme temperatures, these neutron-bearing nuclei remain perfectly stable within the crucible's structure.
Coronal loops remain suspended above.
Advanced electronics are built around stable neutron-bearing nuclei.
And settles. Ultraviolet ribbons lose their sharp brightness. The ionosphere above Earth returns toward its ordinary daytime state. Radio paths recover, and satellites continue through the changing space around the planet. Farther from the Sun, any disturbed solar wind carries the remaining effects outward. Energetic particles become less intense as they spread, scatter.
Solar energy conversion rearranges only the electrons. The nuclei and their neutrons remain completely unchanged.
Expands into a wider and thinner structure. Its magnetic field weakens with distance.
Magnetic fields arise mainly from charged particles, while neutrons remain hidden within the nuclei.
Flow surrounding the planet. On the Sun, the magnetic system does not become still. Convection continues beneath the photosphere. Sunspots drift, rotate, divide, and decay. New magnetic flux may rise into the active region, while older structures slowly relax. Some stored energy has already been released, and some may remain. Observations follow these changes without assuming a fixed outcome. The flare becomes one event within the long rhythm of solar activity.
Primitive solar system matter carries bound neutrons within a diverse mixture of elements.
The upper atmosphere and then declines. Its particles and plasma travel more slowly, shaped by magnetic fields and the solar wind. Each layer responds according to its own density, temperature, motion, and structure. The sun continues to shine with steady, nuclear power beneath its changing magnetic surface. The active region moves onward, carrying the quiet possibility of further change as the solar atmosphere gradually settles into another temporary arrangement.